This class I am going to explain about representation of R, L and C elements in frequency domain. So this concept I am going to explain. So first let me explain the resistor indicated as R. Here the voltage and current relationships that may be in resistor, inductor and capacitor we can represent here. So for resistor the voltage and current relationship is V of t is equal to R into I of t, and in time domain representation the resistance can be represented as like this. This is the resistance, it is V of t, it is I of t. This is the resistance value R. In frequency domain resistance, this resistance, if you apply the Laplace transform for this equation, it will become V of S and R into I of S. So this resistance in frequency domain I can indicate like this. So this is R, this is V of S, this is I of S. So it is frequency domain representation and it is time domain representation. Okay. So in a similar fashion the inductor can also be represented. So let us consider the inductor or inductance. The voltage and current relationships in an inductor are V of t is equal to L into di of t by dt. Suppose it is a inductor, the voltage across the inductor, let us assume it is V of t, and the current that is flowing through this inductor is I of t. Then this is the value of the inductance L. The relation between the voltage and current in an inductor is this one. So it is time domain representation. Next, frequency domain representation. So apply the Laplace transform to represent this inductor in frequency domain. If I apply the Laplace transform, it will become V of S, that is L into S into I of S minus I of 0. L is the inductance here. So it is Ls into I of S minus L into I of 0. It is V of S. And this V of t, if I want to find this I of t from this expression, di of t by dt is equal to 1 by L into V of t. If I apply the integration on both sides, it will become I of t is equal to, it is 1 by L integral V of t dt, and these limits will be minus infinity to t. This concept I already discussed in previous classes. So that is 1 by L into integral minus infinity to 0 V of t dt plus 1 by L into integral 0 to t V of t dt. So this value is nothing but I of 0, initial current, plus it is 1 by L into integral 0 to t V of t dt. So this is the expression for I of t. If I apply the Laplace transform for this I of t, then I of s is equal to, it is a constant, it is I of 0 by s plus, if I apply the Laplace transform for this integration, it will become v of s divided by s. So this is the another expression, that is I of s is equal to v of s divided by ls plus I of 0 by s. This is the another expression. From these two equations, I can draw two networks to represent the inductor in frequency domain. If I use this network, this equation, then representation of this inductor in frequency domain will be as follows. So you see, this is an inductor, it is v of s, and it is I of s, it is ls, it is minus and it is plus. This value is L into I of 0. So if I apply the KVL for this loop, V of s is equal to Ls into I of s minus L into I of 0. So this equation can be represented in network form like this. So it is the frequency domain representation of the inductor, one way of representation. Another way of representation, or I can also represent the same inductor in frequency domain using this equation. Here this is an inductor and this is the current that is flowing like this. It is I of 0 by s. This value is ls and this is v of s. This is I of s. Now this I of s is equal to this voltage v of s divided by ls plus this current I of 0 by s. If I apply the KCL at this point, this current is equal to this current plus this current. This current is v of s divided by ls. This current is I of 0 by s. That means this inductor can be represented in frequency domain, either frequency domain representation, either like this or like this. Next, the capacitor. How to represent a capacitor in a frequency domain? Capacitor. See. So this capacitor, the voltage and current relationship in a capacitor. Suppose this is a capacitor. The voltage and current relationships, it is V of t, and this is the current flowing through this capacitor I of t. Value of the capacitance is C here. Now the voltage and current relationships in a capacitor, I of t is equal to C into dV of t by dt. Or if I want to represent the voltage is equal to that expression, then take the integration on both sides. So integral I of t is equal to C into, it is V of t, and this will be from minus infinity to t. So V of t is equal to 1 by C into integral minus infinity to 0 I of t dt, it is dt, plus integral 0 to, so here it is 1 by C into integral 0 to t I of t dt. I can split this integration like this, minus infinity to 0, 0 to t I of t dt. And anyway, this value is V of 0. Initial voltage in the capacitor is V of 0 plus 1 by C into integral 0 to t I of t dt. So this is the expression for V of t, and this is the expression for I of t in a capacitor. Now if you want to draw the capacitor, or if you want to represent the capacitor in a frequency domain, then I need to take the Laplace transforms for this. If I take the Laplace transform for I of t, it is I of s, that is equal to c into s into v of s minus v of 0 into c. So c into v of 0. Here, if we take the Laplace transform for this expression, it is v of s is equal to, it is a constant divided by s plus it is an integration 1 by cs into I of s. So this is one expression and it is another expression. So there are two ways of representation of the capacitor using these two equations here. So now if I use this expression, now you see it is capacitor, it is 1 by cs, current flowing through this is I of s, and this voltage will be plus and minus, it is v of 0 by s, and this is equal to this one. The voltage across this combination is v of s. So v of s is equal to this voltage plus this voltage. This voltage is v of 0 by s. This voltage is current into the impedance. Impedance is 1 by cs. So current into impedance. So this equation can be represented in network form like this. That too, it is a frequency domain representation because this s coefficient, this s variable is present here. Next, representation of this equation in a network form. So here it is, there are two currents here. One current is cs into v of s, another current is this current. So this one, this is I of s, this is one current I of s, two currents. So it is one capacitor 1 by cs, this value, and the voltage across this one is v of s, is the voltage across this capacitance, and the current is in opposite direction because it is minus sign. So it is in opposite direction. So it is c into v of 0. So this current is equal to this current, or if I apply the KCL at this point, this current plus this current is equal to this current. That is I of s plus c into v of 0. I of s plus c into v of 0 is equal to this current. So this current is equal to voltage divided by the impedance. Voltage is v of s divided by the impedance is 1 by cs. If I bring the denominator to the numerator, it will become cs into v of s. So a representation of this capacitor in a frequency domain, either I can represent like this or I can represent like this. So it is the frequency domain representation of the capacitor. It is the time domain representation of the capacitor, time domain. Okay, so these two are important here. Mainly we are using this type of network here. So we need to remember this network, representation of the inductor in a frequency domain. This is mainly we are using this one, this network. Here, this network mainly we are using. Okay, depending upon the circuit, while we are analyzing any electrical circuit, depending upon the problem or a circuit, we will use either this network or this network in representation of this capacitor. Here also the same thing, we can depending upon the circuit only, but normally we will prefer this network and this network. Okay, now let us analyze using this concept. Let us analyze the RL circuit. Analysis of RL circuit using frequency domain analysis or Laplace transforms. Laplace transforms. Okay, so let us consider an RL circuit. So this is an RL circuit resistor along with inductor which are connected in series. It was supplied by a source, that is V, and this supply is connected to this RL circuit through this switch here, and this switch is closed at t is equal to 0. Whenever this switch is closed, the current that is flowing through this is I of t. Now what I need to find here is, I need to find this I of t expression, or we can also find this VL of t, the voltage across the resistor VR of t, mainly the current through the inductor I of t. This expression I am going to prove that V by R into 1 minus e power minus R by L into t. This expression I am going to prove using this Laplace transforms. Using the time domain analysis, we already proved this. Now I am using this Laplace transform approach to prove this expression. It is for t greater than 0. Okay. Now see, for t greater than 0, let us represent this circuit in a frequency domain after applying this Laplace transforms. If I apply the Laplace after if you represent this network in a frequency domain, it will be V by S, and the switch is closed here for t greater than 0, and this resistor is represented same as the resistance, and this inductance can be represented like this. So this inductance I am representing like this. Either ways we can use, but mainly we are using this one because of the simplicity. Ls in series with L into I of 0. So here it is inductance Ls in series with, it is negative, it is positive, L into I of 0. So it is I of S. To draw this network, we need to find the value of this I of 0. We know the value of L here, R values known value, V is also known value. Only the unknown value here is I of 0. So to find this unknown current I of 0, we need to draw the circuit at t is equal to 0 minus. If I am able to find the current at t is equal to 0 minus, that is I of 0, the same current will flow after at t is equal to 0 plus also, that is after switching action is done, just before after switching action is done, that is I of 0 plus. It is switching action 0, it is 0 minus just before switching action, it is switching action, it is just after switching action. Inductor doesn't allow the sudden changes in current. That means whatever the current that is flowing at t is equal to 0 minus, the same current will flow through the inductor at t is equal to 0 plus also. That is what I am indicating here. So the same current is flowing here and here. So the same current will flow at t is equal to 0 also. So that is I of 0. So at t is equal to 0 minus, if I draw this circuit will be like this. The switch is open position. The switch is under open position. So here this supply is not connected, and the inductor under steady state condition it will act as a short circuit. So this is the current, no current will flow through this inductor, that is 0 amperes. So I of 0 minus is equal to I of 0 plus is equal to I of 0 is equal to 0 amperes. So if I place 0 amperes here, 0 into L, so it is 0 volts only. So the voltage is 0 means it will act as a short circuit. So I can represent this circuit like this. So it is V by S, and this switch is closed here. This is the resistance and this is the inductance. It will act as a short circuit. So this is Ls, it is R, it is I of S. Now if I write this KVL equation for this, V by S is equal to, okay, let me write in another page. So it is V by S for this. V by S is equal to, sorry, I of S is equal to voltage V by S divided by this impedance, that is R plus Ls. If I take this is L as a common, V by L, this S, bring this S the denominator, S into S plus, it is R by L, R by L. The same expression I am writing like this, by taking the L as a common in the denominator and S should be placed here. Now it is like A divided by, if I do the partial fractions for this, or otherwise the same thing, I need to find I of t here. So I need to apply the inverse Laplace transform for this expression. So I need to use the partial fractions here to apply the inverse Laplace transform to find this I of t. So what I am doing here is V into R by L divided by S into S plus R by L, and here it is V by R. This R and this R will get cancelled, so V by L into same thing will appear here. So it is V by R into S plus R by L minus S divided by S into S plus R by L. So this S and this S will get cancelled, same R by L will appear here. So this can be written as V by R into S plus R by L. This S plus R by L will get cancelled, so it will become minus 1 by S minus this S and this S will get cancelled, so it will become 1 by S plus R by L. So it is I of S. If I apply